It's my pleasure to welcome Ryan Reich of Harvard University, who will speak to us today on Beilinson's How to Glue Perverse Sheaves.
Well, thanks, David Massey, and thanks to the Worldwide Center for inviting me. So this paper of Beilinson's is famous not only because of the theorem in its title, which it proves, but also because of the several implicit constructions, very beautiful elementary constructions of nearby cycles, which it contains, which are mentioned in the paper, but are not made explicit there. And since these are very useful theorems, I decided that I should produce some elementary proofs of them. As a result, this is sort of an expository talk. It's mostly about theorems that are originally due to Beilinson, and the only thing that is original to myself is at best the presentation and perhaps the proofs, but I suspect that these would also have been known to him. All right. So in terms of context, in order to save time, I will assume familiarity with basic notions of perverse sheaves to the level of theorems, not deep theorems in BBD, but just basic foundational theorems in that paper. Also, in order to save on technicalities, I will work in the context of the classical topology on complex algebraic varieties. As Beilinson discusses in his paper, it's perfectly possible to formulate all of this in terms of, for instance, the Étale topology and L-adic sheaves, or in terms of D-modules. But I think the language is clearest and with fewest complications when you just work in this setting. All right, so the outline for what I will talk about is the following. First, I will discuss nearby cycles. All right, so this will be sort of a review definition, since it won't make much sense if you have no idea what it is, but at least it will be self-contained enough for the rest of the talk. And then I'll talk about construction of nearby cycles. And the relationship of this construction to Verdier duality. And this is one of the great immediate consequences that comes out of Beilinson's setup, that the nearby cycles functor is in fact Verdier self-dual. Next, there's vanishing cycles, and the eponymous gluing theorem. And finally, in formulating the gluing theorem, there's a new functor that's introduced, which Beilinson terms the maximal extension functor. And since this thing is quite mysterious, I at least had never seen it, and I'm told it was new, at least 28 years ago it was new. So I think it needs a little bit of explanation of itself. So to begin with 1. So my notation, I'm going to call, say, d of x the constructible derived category. On x. And I won't worry too much about what that means, other than that it makes things work. Likewise, m of x is going to be the heart of the perverse T structure. This is the abelian category of perverse sheaves.
X is complex algebraic?
Yeah, so I guess maybe I'll make that notation in a minute when I talk about the rest of the setup. Yeah, abelian. Right. Now, as mentioned, X itself is a complex algebraic variety. And the setup for nearby cycles is a regular function, f from x to a1. So maybe actually I should write it like this. This induces both an open set and a closed set. Let's call the closed set Z, and the inclusions I and J, as usual. So, in this setup, to construct the nearby cycles functor, what you do is take the universal cover of this, which is topologically just the punctured complex plane. Let's call this unimaginatively A1 minus 0 with the tilde, and lift it to U like that. So let's call this map V. This square, actually all of these squares are Cartesian. All right? And the definition is that psi f is going to be, let's get the order right, I star, j lower star, v lower star, v upper star. And this goes from d of u to d of z. All right. The fact
because I know this so well, I know what u is and what z is, but I'm not sure that they do.
I'm sorry. It was implicit in the fact that this is Cartesian, but what I meant by that was that U is the set where f is not 0, and z is the 0 set, hence the notation, I suppose. So z is some divisor. It's a mistake that I made in an earlier version of this paper that it cannot be an arbitrary Cartier divisor. It has to be a principal Cartier divisor. Otherwise, this does not work so well. So the fact that this goes from the constructible derived category to itself is actually a theorem of Deligne. Namely that R psi preserves constructibility. All right, now, as a consequence of that, you can extract from this functor something a little more specific, and which will actually be the main object of this whole discussion, the unipotent nearby cycles. All right, and the way that works is very simple. Psi f is naturally a direct sum of some unipotent part plus psi f of not equal to 1. Now, what does that mean? Well, I have to say what actually the unipotent, the thing that which is unipotent, and that's a certain operator arising from the action of the fundamental group of this punctured plane. So pi 1 of a1 minus 0, which is non-canonically z. You could choose several generators, but you choose one. And this acts on this nearby cycles functor because it acts on the universal cover by deck transformations, but this thing is invariant under that. All right, so let's call T the action of 1, and I will never talk about the action of anything else. So in this theorem, this is where T minus 1 acts nilpotently, or maybe I should say acts nilpotently on each value of this functor. There isn't a global number which makes the whole natural transformation vanish. And here, T minus 1 is invertible. So since this actually holds of the underived functors, you can, of course, stick r's in front of them, since it turns out they will all be left exact as a result. This is a unique decomposition, and it's effectively proven by linear algebra. This is a rational Jordan decomposition. This is the part with eigenvalue 1. This is the part with any other eigenvalue. All right.
Does that require that the base ring is a field, or can you do that with?
Well, it's got to be a field here, and this is sort of implicit. I mean, it's explicit in the paper, but I should have mentioned it somewhere over here, that these are all over some field. Otherwise, I can't really do the Jordan decomposition.
Just for someone who doesn't know this stuff, a kind of intuition, like if x is c to the n and f is, let's say, a homogeneous polynomial.
Mm-hmm.
And you have a Milnor fibration. So does this have something to do? I mean, is this something like the homology of the Milnor fiber? Or not?
Is what?
I don't know, C somehow related to that. I mean, does it have anything to do with the Milnor fibration?
Yes.
What?
So I hesitate to admit that I'm not up on the topological connections of this, since I know David is, maybe he can help me with this after the talk.
Well, I can just say quickly that the stalk cohomology of the nearby cycles is the cohomology of the Milnor fiber at that point. So it's a constructible complex of sheaves whose stalk cohomology gives you cohomology of the Milnor fiber at each point tells you how it patches together. And so yeah, the action, the monodromy action is of course just you let F go around, the value of F go around the small
That's what I was
circle.
more or less trying to understand what you're talking about.
Yeah.
Okay. Yeah, there are probably more elementary ways of making this definition, but this is the most expedient for getting to some of the stuff later. All right. So now that I have the unipotent part, I can express a couple useful triangles in the derived category. And since I'm going to need them, I'm going to put them over here. So first of all, there's this one. I'm going to habitually drop I lower star because I've been doing it for so long. But if something seems to be on the wrong space, it's because I forgot that. So for actually, I'll just say there's a triangle of functors where you can plug in anything you like to them. And it goes like this. All right. This one can be seen relatively easily from this definition. Well, at least part of it can be seen relatively easily. This map is, this map can be obtained just by some natural map involving this adjoint pair of V lower star and V upper star, and it's not too hard to see that it makes the 1 minus t go to 0. And to actually obtain a triangle, you do some homological algebra tricks.
It's topologically, it's the wing sequence.
So the other one, maybe I should have put this first, but it's not going to be used until later, is the one that defines the vanishing cycles. Or at least the unipotent part of the vanishing cycles. If I took out the superscript, it would also define the non-unipotent, the entire functor. And this one can also be constructed by some homological algebra tricks, which actually makes this thing, which is just the cone of a triangle, actually a functor. All right. It turns out, in fact, that it's more helpful to rewrite these in another order because of a theorem that I'm about to mention. Because although you define the nearby cycles this way, this isn't really the right position to consider them in. The correct position is that you should shift it by 1. So this sends complexes which are perversely in degrees less than or equal to 0 to complexes on Z, which are perversely in degrees less than or equal to 0, and also sends perverse sheaves themselves to perverse sheaves themselves. Now, although I quoted a theorem of Deligne earlier, I'm not going to quote a theorem of Gaber, but will in fact prove this directly. It follows immediately from triangle 1. The key point is that since Z is a Cartier divisor, the inclusion of U is an affine morphism, which makes J lower star T exact for the perverse T structure. And as a result, I upper star J lower star is right T exact. Just like I upper star is always right exact. And so if you take that first triangle and you string out the long exact sequence of perverse cohomologies, what you get is something that typically looks like this. So there will be first cohomology, R epsilon F minus 1. Well, there will be something in here, some complex A, mapped by 1 minus t to the same thing. So this is a typical portion of the long exact sequence, but since this functor is right exact, this term is 0. And since this is an exact sequence, I now have a nilpotent and surjective map, which would have to be 0. So since it's surjective, this term is 0. So that means that the first claim is proved. As for the second claim, if I have some perverse sheaf, then I just do the same thing except below 0. And the reason that works is that now I can say more specifically that this I upper star j lower star of m is actually in perverse degrees -1 and 0. So I end up with another typical portion of the sequence, h minus 2 now. And now the h minus 1 terms one minus t, and then same thing, and then so on. And again, this vanishes, and so this is injective and nilpotent. And 0. And that finishes the proof. So this is sort of a pre-theorem of Beilinson's, actually. It's sort of implicit in all the considerations there, and I think the use of the unipotent nearby cycles functor is basically inspired by the way he does things in his paper.
So, at least at this stage, this proof wouldn't allow you to prove that the full functor R psi takes perverse sheaves to perverse sheaves, right?
So
the unipotent part, but then you do all the tensoring and twisting. And,
right. So
yeah.
it's just elementary considerations show that you can express R psi as a direct sum of parts having where t has eigenvalue lambda, and those things are themselves equal to unipotent nearby cycles on something tensored with some line bundle, not line bundle, but local system of rank 1 having monodromy equal to minus lambda to cancel it out, and then you express, now you've expressed full nearby cycles in terms of unipotent nearby cycles. And using some abstract nonsense, you conclude that in fact these two properties mean that this functor is actually t exact, not just right t exact. All right, so this is the first nice consequence of the perspective in Beilinson's paper. So that's number 1. Oops. So now we'll go on to give a better definition than this, which is, after all, sort of awkward. No one wants to pass to infinite étale covers, which aren't even algebraic.
doesn't bother me. Might bother Steve.
All right, well, some people would like to do it, but certainly it forces you to leave the algebraic world, and that gives some people the shivers. And after all, this definition is pretty abstract. It's all derived functors and Flask resolutions at best, whereas now that I've proved that this functor actually preserves the abelian category of perverse sheaves, it would probably be best if I actually gave a construction inside of the abelian category rather than having to leave it, go into derived category complexes, and then come back. So, number 2. So as always, anytime I write M here, this is going to be a perverse sheaf on U. And to save notation, that thing, the shifted nearby cycles, is just going to be big psi. Oops. All right, and this goes from m of u to m of z. Now, the clever idea, which is in Beilinson's paper, is to introduce this local system LA. So its fiber, this is a local system on A1 minus 0, which was in that picture that is no longer there. And this has fiber, some a-dimensional vector space, and monodromy, some Jordan block. And for technical reasons, and to keep consistent with the paper, I will put 1s above the diagonal, or minus 1s above the diagonal rather than the usual 1s, but it's the same thing. And so the principle of this construction is basically going to be that you can spin out the nearby cycles by twisting with this thing to a high enough degree, and then comparing with certain well-known geometric functors. One lemma which will be useful is that this thing is highly resistant to alterations. So this is the inverse local system where I replace this matrix by its inverse, and this is the dual local system where I replace it by its transpose inverse, or its transpose. I mean, anything you can do to this matrix will leave it similar to itself. So in addition, there's a property that will result in showing that this functor is self-dual, which I'll just state now. If you have any complex of sheaves on U, then the Verdier dual of it twisted by the pullback of this local system is isomorphic to the dual of just a complex twisted by the pullback of this local system. So this is sort of a generalization of the fact that it's isomorphic to its own dual. If I didn't pull back, if I did this on A1 minus 0 and didn't twist by anything, then this would just be that statement. All right, so I'll just leave that alone. It's mostly formalism to prove. The interesting thing that you do with this is that let's denote a certain natural map by alpha. This is a map from J lower shriek to J lower star, where I apply it to M, but I also twist by this local system, as I said. Then there is an injection from the kernel of alpha into the nearby cycles of M, not of M twisted by anything. And this is an equality if A is very large. If you want to compare this to Beilinson's paper, this is effectively what he calls the key lemma. At least the argument in here is closest to the contents of that lemma. And as he observes in the comments at the end of the paper, this theorem can be extracted from whatever he writes there. The proof of this relies on a comparison between this useful triangle and the other useful triangle, going from J shriek of M to, well, J shriek of something to J star of something. All right, this is just some six functors formalism mentioned in BBD among many other places. And if you notice, it has the same cone as this triangle. Actually, if I shifted this triangle so that it agreed with the notation I have here, it would actually be exactly the same cone. So if I plug in the appropriate object, this map is alpha. And so the kernel of alpha is the same thing as the kernel of 1 minus t acting on the nearby cycles of this thing. And that's much easier to manage. The reason for that is because this is a local system, that pullback that appears in the definition of nearby cycles untwists it so that you end up with a nice equality. Not LA, but let's just call it straight LA. This is just a vector space of dimension A having that action of the monodromy on it. And this is, of course, isomorphic to just a direct sum of copies of this with itself. Well, now I can construct inclusions by hand. So if I have something in here, I'll just write this in terms of elements. The action of T sends something of the form x1 through xa to tx1 minus tx2, tx2 minus tx3, and so on all the way down to txa. All right? And therefore, you can check the kernel of 1 minus t is given by equations of the form xi plus 1 is equal to 1 minus t inverse xi. And so just stringing it out inductively, you end up with xi is 1 minus t inverse to the I minus 1 of x1. And since there's this exceptional case all the way at the end, you also have that 1 minus t to the a x1 equals 0. So since this all depends only on the first coordinate, I can define a map u, let's say, from nearby cycles into, not into that, but into this, just by sending x to x 1 minus t inverse x and so on. And this contains the kernel of alpha, namely it contains the ones which actually have this last coordinate equal to 0. Also, if A is sufficiently large, I did say that 1 minus t acts nilpotently on this part. That was the point of constructing it. So if A is sufficiently large, the last term will actually be 0, and this will actually coincide with all those objects satisfying this equation. I'll just write for all x. You can be rigorous about these elements, but this is there's no need to get pedantic right here. All right, so that settles the isomorphism. You can actually also check that now the action of T, the monodromy, is given by the Jordan block, or almost. Because if I take this thing, let's call this JA for Jordan block. If I take JA and apply it to x 1 minus t, or t inverse x, and so on, I will get x minus 1 minus t inverse x, and so on. I will not write the others. They all look similar. And this is t inverse x, and so on. And the subsequent ones will have powers of 1 minus t inverse multiplying them. And you see that this is actually almost the action of t. It's the action of t inverse. And so I've actually defined sort of the wrong map. What I should do is compose it with the isomorphism between LA and LA inverse, and that will take care of that. And that finishes this. This is the elementary construction promised in Beilinson's paper. Now, that's only half the story, because another remarkable thing which falls out of this is the fact that that the nearby cycles functor is actually Verdier self-dual, like I said. And the way to see that is simply to look at what I haven't mentioned yet. So I've said that this is the kernel of alpha A for A very large. If I conjugate this with duality, I will end up with dual of psi of the dual is equal to the co-kernel for A very large. All right, well, this suggests the immediate strategy that if I should show these are equal. And to show these are equal, I should show that those are equal. So let's do that. At least when A is very large. All right, well, this is just observing that although this thing is not a direct sum of all right, so this local system is not actually a direct sum of one-dimensional local systems like the line was, but it does have a filtration, so I can at least say that it contains smaller copies and has others as quotients. And so I'm just letting A and B be whatever they need to be at the moment. This is true for any positive numbers, A and B. This is where I sort of include a Jordan block inside a larger one in the upper corner, and this is where I sort of include it in the lower corner. Now, if I pull this whole thing back and I tensor it with M, then what I obtain is what I obtain is a sequence of things that look sort of like this. And then I could apply either J shriek or J star to it. And I end up with two short exact sequences. I'm not going to write all of these terms again and again. A plus B, J shriek of LB, and likewise the same thing with J star. Aha, but there are natural maps, and so I get a map of short exact sequences. And by the snake lemma, I obtain, so this is alpha A, this is alpha A plus B, and this is alpha B. So I get kernel of alpha A going to kernel of alpha A plus B, going to kernel of alpha B, going to co-kernel of alpha A, co-kernel of alpha A plus B, and co-kernel of alpha B. And for what it's worth, it's exact on the end, not that it matters. So I did argue that for a sufficiently large thing in the exponent of alpha, this kernel is equal to the nearby cycles functor. So if if A is really large, then these two are both equal to the same thing for A sufficiently large. Likewise, you can sort of just apply a double dualization argument to conclude that for B sufficiently large, those two are equal to the same thing. So I suppose that those must also be isomorphic, and that's the rest of the proof. So in conclusion, maybe I should mention this explicitly since it's a really slick argument for a pretty deep theorem. This commutes with Verdier duality. Now, if you wanted to check this against Beilinson's paper, this is not at all the way it looks in the paper, although I believe it's equivalent to what he writes there. He has this formalism with some sort of two-sided limits having to do with subquotients of some infinitely filtered vector space. This, unfortunately, this seems not to have been adopted anywhere else, and therefore neither I nor anyone I know of has become familiar with it. So rephrasing it in this way seems to make it clearer.
You meant to put the isomorphism on the next arrow, but
Yeah, oh, I did totally mean to put on the next arrow.
I think you use implicitly that the categories are tinian, right? To know that if two things are abstractly isomorphic and one injects to the other, then they're actually
Well, in this
maps an isomorphism.
so in this case, what I've actually shown is that they're both contained inside of.
Yeah.
They're both contained inside of this one object.
Yeah.
So what I've shown is that these containments one factors through the other, and that eventually their images are equal. So here I'm not actually using the Artinian property. There's a more general statement in my paper which does use that property. But I think this follows in an elementary way just from the theorem which was over there. All right. So speaking of that more general statement, one could do, with a little bit more setup, the following thing. The kernel of the map from J shriek of so you could tensor with LA at the beginning and then drop a degree by just taking the quotient similar to this short exact sequence here. And then you'll end up with a kernel which is slightly larger, but this also stabilizes. And this is also equal to the co-kernel of something where you raise a degree instead. And this is, therefore, self-dual. And this defines a functor, which is denoted psi, or as I denoted psi un sub f. This is the maximal extension functor. All right. So it should really be called the gluing functor based on its role in the next theorem, but so it is. And so this one is completely mysterious, and I will try to explain it later. But let's get on to the gluing theorem. All right, so that's number 2. Number 3. All right, so the fundamental fact about this maximal extension functor is that it satisfies 2 short exact sequences. I'll call these actually short exact sequences 3, and I'll try not to erase them. They are this, and let's give all of these maps names: alpha minus, alpha plus, beta minus, beta plus, and the property of these maps is that alpha plus, alpha minus, which goes from J shriek to J star, is the canonical map. And beta minus, beta plus, which goes from nearby cycles to itself, is 1 minus the monodomain. So from here on, you no longer need to use any specific properties of perverse sheaves or of nearby cycles to do anything. Actually, the rest of the gluing construction follows completely just formally from this setup. Nonetheless, it is not done producing deep constructions because you can define the vanishing cycles functor. Now, this is supposed to be the same as this one, at least up to a shift, but I haven't proved that yet. I'll get to that in a moment. It's defined to be the cohomology sheaf of the following complex. Now, this is not like any sort of sheaf cohomology. This is just homological algebra. It is, oh, there it is. All right, so it's actually exact on the ends. The only place it's not exact is in the middle. The terms are given by the alphas in this thing gamma. So gamma is, for instance, gamma minus goes from j shriek of j star of f to f, and this is again the canonical map, just given by a junction, since this is a left adjoint to j star, and likewise gamma plus. All right, so this is all completely explicit and elementary. Now f, by the way, is going to be anything in m of x, trying to separate my notation. M lived on u, f lives on x. And so you construct this functor as the cohomology of this complex. It's not hard to see that it turns out to be an exact functor. It's not defined at the moment for anything other than perverse sheaves, but that's OK. We're only talking about perverse sheaves now. And using it, you can get to Beilinson's gluing theorem. All right, so, oh, I should mention before I get to the gluing theorem that this thing also has structure. So there is a pair of maps from nearby cycles to and from the vanishing cycles. This one I'll call U, this one I'll call V, and this one is just in reference to the sequence. These are defined by beta plus 0 and beta minus 0. I apologize for the sort of ad hoc pairing notation. It's supposed to indicate that you apply the various maps to the components and then add them. So this should be it should be no mystery, given that this is supposed to be the vanishing cycles. What these are supposed to be, well, there is a map from nearby cycles to vanishing cycles, and this will turn out to be U, or at least U of 1, since I shifted. All right, so now I can get to gluing data. Gluing data consists of 4 pieces: something on U, something on Z, and 2 maps. Well, something on U is supposed to represent J star of F. Something on Z is supposed to represent the vanishing cycles. And U and V are supposed to have the same relationship as these U and V's do. The relationship is that this composition is 1 minus T, as you can see from that.
So are FU and FC perverse?
So yes, this is the this is sort of the beauty of this particular gluing construction. There are other gluing constructions in sheaves. You can do something similar with I upper star, for instance, rather than taking vanishing cycles. But this does not preserve perverse sheaves, and so it requires you to leave the category. So it does not have good exactness or duality properties. This, on the other hand, is just a linear algebra construction. I won't do that construction here because it has nothing to do really with perverse sheaves, and I would like to talk about the vanishing cycles. But what you get, so as I indicated, there is a forgetful map sort of from M of x to the set of gluing data. And the theorem is that there is an inverse map and where, let's call it G sub f, it takes this pair of perverse sheaves together with their two morphisms and constructs the cohomology of some other complex, namely this one. So this now is going to be beta plus combined with u, and this is going to be beta minus combined with minus v. And that's why you needed to keep these things being perverse sheaves, so it made sense to take the kernel of something modulo the image of something, operations that only exist in abelian categories. So to show that, I mean, I've given the maps explicitly, so it is presumably a matter of computation to show that they are inverse to each other. Beilinson has this very elegant axiomatization of what computations you need, and it would take way too long to do them, so I won't. That's not really the point, because this doesn't have anything to do with nearby cycles anymore. It's just linear algebra making this computation work. The question is, I have now, in the course of discussing this theorem, introduced not one but two new functors, and I have no idea what either of them are. That's not really good policy, considering that I went to such great lengths to explain the nearby cycles. Let's also explain the vanishing cycles. It is, in fact, the vanishing cycles. And in that triangle 2, the map from R psi to R phi is u, or u of 1, given the shifts. All right, now, the way to do this is more or less to write down the octahedral diagram 2 or 3 times, which isn't the most pleasant of prospects, but actually turns out not to be so bad. So the thing is, by definition, let's define, in this complex, let's make K the kernel of that map. So we have the short exact sequence 0 to J shriek J star F to K to phi to 0. Well, short exact sequence of perverse sheaves corresponds actually to a triangle, and so I can write down an octahedral diagram involving that triangle. All right, so the way this diagram is constructed is we have J shriek J star of F to K to phi to, I'll put in the terms and then explain why they're there. So this is my favorite presentation of the octahedral diagram. It's the one that is proposed in BBD in place of an actual octahedron. All of the lines are triangles, and all of the triangles are commutative, and hence not triangles. So this triangle corresponds to that exact sequence, and this map is the projection map, since, all right, shouldn't have erased it, but K was contained inside of a direct sum similar to this one, and the second term was F. And this is the projection onto F. And from the definition of that complex that K appeared in, it's immediate that, in fact, this triangle does commute, so there is an octahedral diagram like this. And if you examine this portion of the diagram, what you conclude is that C of minus 1 is perverse. Just doing some computation with perverse cohomologies gives you that immediately. Actually, it's better than that. It fits into an exact sequence. So you have minus 1 to k to f to 0. And I did say I would try not to erase those triangles, and there I did erase them. So,
It was common, and I thought, well, it's time.
but if you're in your mind's eye, you imagine those triangles, you will realize that this is supposed to be the kernel of that map that I denoted beta. No, it's actually beta minus. And this, as appeared in the triangle, is the same thing as the nearby cycles functor. So actually, I can be more specific about what's here. Excuse me, of 1. All right. Now, well, I'll leave that for a moment. I know that the last term of this linear triangle is I star of f because this is the natural map, and in fact, there is a canonical triangle, one of the 6 functors things again, that has the cone equal to I star f. So it would appear on the face of it that what's here is the same as triangle number 2, except shifted by 1. I have not actually told you what any of the maps are in it yet. So to rectify that, maybe I should suggest that we work backwards a little bit and compare it to what you would get if you actually started with something involving this triangle and then tried to deduce this octahedron from it. So if you draw a similar diagram starting from this commutative triangle, you end up with so I'll call this one arp psi to emphasize that I'm talking about something coming from here. This is still a commutative triangle. And if I fill in the rest of the diagram, then what I end up with is this something over here that I'll call k prime, and that. So that is to say, this octahedron propagates from that commutative triangle the same way this one propagated from that triangle. All right, well, I'm not going to go through the details of this because it is really just sort of abstract nonsense, just playing around with the Beilinson categories and chasing diagrams. But in fact, you can see that k prime is isomorphic to the kernel of, what was it supposed to be? I didn't write it down. What was that thing called? Alpha plus minus gamma plus, I think, was what appeared in there. So this is the same thing of which k was the kernel. So that is to say, you can deduce that there actually exists a map. It goes like this. You have 0 to you have this short exact sequence coming from this triangle just by shifting. I know that if I shift, this becomes perverse because I already proved that theorem. And down here, you have one of the sequences that it's in the perennially disappearing pair of sequences over there. So these two are equal, or at least isomorphic. There is a natural map from f to j lower star, j upper star of f. And I claim that this extends to a map of extensions. And that amounts to just checking that a certain square commutes if you look off the end. That is, if you express both of these as some map from f to this translated by 1 and that to this translated by 1, that those two maps fit into a commutative square involving this natural one. And that can be done. As a result, what you find is that not only is k prime the same as k, but also both of these maps are the same as both of those maps. And so actually, these octahedral diagrams are exactly the same. And if I rewrite them a little, I can also figure out what u is supposed to be. So the problem with this diagram is that u sort of goes off the edge. So if you'll indulge me, I will write yet a third octahedral diagram, which is surely a record somehow. What I do is just rotate all of these things. You can imagine somehow that this is correct, largely because none of the triangles are nonsense. Actually, if you want details, I have them written down, and I can give them to you at some point. So this is not a typical octahedral diagram in that it doesn't really display all the properties that one should, but it has the same setup. Namely, these things are all still distinguished triangles, and all the actual triangles are commutative. So if you compare this to that, what you find is that whether I put k or k prime here, this map doesn't change. So I'll just write OK. And likewise, this map is OK. They correspond to these two maps here, or those two maps up there. Well, this is a triangle with perverse sheaves. So actually, this is a short exact sequence. And so this is its co-kernel. And that's uniquely determined by the first map, so it's OK. And this is also a short exact sequence. And this is its kernel. So that one's OK. But now I have factored this thing, which is either u or the natural map, the one in triangle 2. And so it must be the composition of two things which don't depend on whether I write k or k prime here. So in fact, u is equal to the natural map. And that finishes that proof. So unfortunately, I do not have enough time to talk about what the maximal extension functor is. I feel less guilty about that than skipping the vanishing cycles functor, since at least one has heard of that before this talk. Basically, I'll just tell you what the result is, that those two short exact sequences that are still not there uniquely characterize this functor, in the sense that if you have some functor, xi, sending perverse sheaves on u to perverse sheaves on x, and if its values extend the input, and if it satisfies those short exact sequences with the conditions on the maps, then in fact it's equal to the maximal extension functor. This is the sense in which it's the maximal extension functor. What those two sequences do is they prescribe what the stalk and the co-stalk, I upper star and I upper shriek, of this thing are over z. And it turns out that in comparison with the j lower shriek star thing that you find sometimes, which is called the minimal extension functor, these stalks and co-stalks are perverse rather than being perverse after shifting. So instead of being very small, they're actually as large as they could possibly be. So I hope this has been at least entertaining. I think this is a very beautiful construction of some functors which make no sense to me as their definitions are given. And I'm glad to have had the opportunity to present it. Thank you.
I have a whole list of questions, but I'll let other people go first. Anybody else have a question? Questions? Comments?
Just trying to figure out why that's an octahedron, and I finally counted 8 triangles.
Oh man! All right. So this is one of these things from VBD that I was assuming that the audience has seen, and yeah, I mean half the octahedron isn't in that picture, unfortunately. Yeah, there's a more typical way of drawing it involving taking a flattened upper half of the octahedron and a flattened lower half and putting them side by side, and that actually looks sort of like an octahedron. But this one, I think, is certainly much faster to draw.
I've never tried to draw it in a paper. You try to draw other things to avoid it, like this. All right. Are there other questions besides mine? Okay. somewhere, I know that you need that your base field is algebraically closed, but I'm not sure where you need
Right.
it.
So
Is it easy to say?
Oh yeah, it's very easy to say. I only need it in one spot. So it was this thing that I wrote earlier when you asked about the nearby cycles functor being exact on the entire derived category.
Right.
So there's this decomposition I wrote that
Yeah, the direct.
arp psi f is isomorphic to the direct sum of arp psi lambda, where here t minus lambda is nilpotent.
Oh, well.
And so this is clearly a use of algebraic closure because
Right.
you need to have all those eigenvalues.
Right.
It's the only spot you need it.
Okay.
Everything else is elementary reasoning.
Okay. I usually like to deal with analytic spaces and maps, and at some point you definitely used affine morphisms. So, but I'm pretty sure that all of this works complex analytically. I'm pretty sure. Am I wrong?
Well,
I mean, the proofs would be, at least that one proof would be different.
so having broken down the prerequisites far enough that I could state them in a short list, all you need is that J shriek and J star are exact, or at least T exact. So if in the analytic setting you
That's
Yeah.
true in the analytics.
so then it still works. That's the only property of perverse sheaves that's really essential.
Okay, so something fails, and it was in your paper, and I don't remember, something fails for, and you mentioned that it fails for abstract Cartier divisors.
So the problem
What is
is,
it that doesn't patch well?
yeah,
Something?
so it doesn't patch well. The problem is
That's
that,
the nearby cycles, the vanishing cycles, both?
yes, it's the nearby cycles. The vanishing cycles, I mean, the same problem would happen because of this triangle.
Right.
But the problem is if you have,
Because there's kind of no natural, from a topological point of view, there's kind of no natural choice of which Milnor fiber you're taking each place, probably. Probably. Okay,
so-
I'm sorry. Yeah.
So I can't give you this example right here because I don't remember it
Right,
because
I remember.
it was in the paper
Yeah.
at one point, and then I commented it out because I was told that Migliorini and Trang have a paper with this as an example in it, and so I just cited that forthcoming thing and left it to other people to read about.
Maybe
So
I'll
I don't
just-
remember what this example is anymore.
Maybe I'll just ask one last question that Alex might be able to answer better than you, because it's a topological question. So I don't want to keep everybody with all my questions, but so when you have that local system, LA, and it has the monodromy that's a Jordan block, but with -1s on the diagonal, I wanted to write that as kind of the Milnor fiber with its Milnor monodromy of some isolated hypersurface singularity. So, but I don't know enough examples. Alex, presumably, since you said that topologically you're not so good at this, presumably you don't know. Do you know of an isolated hypersurface singularity, a class of them whose fiber, would be, C or K to the A, and then whose monodromy has the -1s, would be that modified Jordan block? I don't.
I should point out that the -1s are a technical device. I put them in because at some point in the paper I wanted to
whatever.
not get rid of some minus signs.
Stupid, like, x to the n.
But that's diagonalizable, right? If it's homogeneous, a homogeneous polynomial's monodromy is diagonalizable, so it's not going to have the Jordan block. It's just going to have, and you're going to have, yeah. Right, it has finite order. It's not going to have a nilpotent part, a non-trivial nilpotent part. Well, I want you to think about this at dinner. Because I want to know. Because I understand, well, because if there were such a thing, then See, I'm used to kind of adding, you have something in some variables and you look at something else in some other variables and you end up with the nearby cycles of this. It's the tensor of what happens here and what happens here. And so I want to know if that local system actually appears, kind of comes from this kind of construction that I'm more familiar with. But that means I need an isolated singularity that has that block for its Milnor monodromy. So
what kind of polynomial now would be?
I don't care. It doesn't even have to be polynomial. It could be analytic. But it's you have an hour and a half, 2 hours to give it to me. All right. I didn't mean to act like you couldn't possibly know the answer.
No, I'm afraid I actually don't know the answer. That's perfectly all right. I am deep into the abstract end of this subject.
Right. That's what I figured. All right. Are there other questions or comments? All right. Well, let's thank Ryan again.
Thank you.